the first time that I am broadcasting this. So for those of you who I haven't met, my name is Olzhas Sissenov. I am KNM's technical manager, and I am streaming to you guys all the way from Russia, from Moscow. Welcome to the show. In today's topic, we're going to have a couple of guests from Repsol, and they're going to walk us through the project that they had here in Russia, in Western Siberia. It was a pretty interesting multilateral extended reach drilling project, and the guys are willing to share with us the challenges that they come across, the observations and learnings. Before we proceed, just the typical standard stuff. Well, I forgot to introduce myself, right? My name is Olzhas Sissenov. I've been with KNM for the last 9 years. I was a drilling engineer in the beginning, and then in our headquarters in Houston, and then I moved to Middle East, to our Abu Dhabi office. And last year, in the middle of pandemic, I moved here to Moscow, and now I'm supporting the operations in Russia and the nearby countries. My background before KNM was mainly directional drilling. Spent few years with Baker Hughes, and then another few years in directional drilling with DNM. Well, that's about me, right? The guests, I have two guests today. They will introduce themselves, and yeah, I think we're ready to rock and roll. So I will. Before we continue, guys, please don't you worry. There's nothing wrong with your site. You don't have a double vision, double seeing. We have two guests. Those are twin brothers, Artur and Erik. Please, stage is yours.
Hello, Olzhas. Hello, everyone. Good day, everyone. Yeah, who is joined? Yes, we are glad to join this broadcasting, this pre-tower with KNM Technology Group. From our side, this is also the first experience, and we do really appreciate such an opportunity to go live with KNM. So we greet everyone who is joining today our pre-tower meeting, and quick self-introduction from our side. Myself, Erik, and my brother Artur Abalian, as Olzhas mentioned. We do both working together with Repsol. We both holding the master's degree in petroleum engineering from Watt, and with Repsol we've been already more than 6 years, with mainly drilling engineering experience from operator side, working globally around the world at different projects. And in Russia, our experience was focused around exploration and development drilling, and specifically of horizontal, multilateral, and extended reach wells. One of the cases we're going to be discussing with you, with everyone today during our session. And before we continue with the main presentation, just a brief note on safety side. Just want to highlight that it's been a couple of days how in Russia the COVID-related restrictions, and specifically lockdown and quarantine measures, has been reinforced and brought back in place. That's due to worsening of the general COVID situation in the country, especially in the capital and all the rest cities. What we want to encourage everyone and just follow the recommendation of local health regulators and WHO, and we want to wish everyone to be well-being and staying healthy. On this note, we would like to continue. I'll just see if that is okay with the presentation.
Absolutely, yes.
Right,
I forgot to mention to the rest of the audience that we've been on a lockdown since yesterday. So instead of being in a nice studio that we have arrangement with, we have to broadcast from like I'm broadcasting from my living room. But anyways,
Yes.
I would like to join the safety moment that the Artur and Erik brought up, and wish everyone, to avoid all those COVID-related issues. Okay, Artur, Erik, stage is yours.
Yes.
Please
Now we
proceed
can
with
all
your
see
slides.
the slide pack that we have prepared. Um, just a little bit introduction, the background of the project. We're going to be talking about the appraisal campaign about the two wells that Repsol drilled in 2020. And that is a shallow extended reach project that was done in or performed in Western Siberia. We'll start with in introduction of the geological environment of operation. So to mention that from this point of view, we were operating within normal pressure and temperature regimes. The temperature gradient was around 4 degrees per 100 meters, and our reservoir was normally pressured. We did not encounter any sweet or sour gases in our reservoir, and the key and specific feature of that project is operating in a shallow depth environment. As you can see, it's 777 meters of true vertical depth subsea. At the right side of the slide, we can also see the cross section. In this regards, our cross section is presented with clays and claystone succession. It's quite uniform, not presenting any anomalies. The formation, the reservoir formation itself is very thin, or 14 meters, which also poses one of the challenges to the project. Having the gas cap above the reservoir and water aquifer underneath. On the bottom of the slide, it's good to share with you this simplistic sketch of the reservoir, which also gives some understanding of the reasons behind designing of such wells that we are talking about, extended reach type. And the reservoir particularity is having the oil contained in the so-called sand lenses, which in its turn are distributed within the main claystone massive. And that's basically creates the main idea and objective of increasing the reservoir exposure. And we have approached that by means of drilling more meterage, having more horizontal interaction of the well, and increasing the drainage area. Expanding more on the subsurface part, we share with you the geomechanical overview. Here at the slide, we can see two basic features. On the left-hand side, we see the aerial view of the stresses distribution. The prevailing stress regime is a normal stress regime with a dominant vertical stress. For the horizontal stresses, we have the negligible anisotropy. So basically meaning that our horizontal stresses are equal in all the, more or less equal, to be correct, in all the directions. And that's also the specifics of the geological environment. On the right-hand side, we can see the well-bore stability plot. Talking about the just describing a little bit the plot we are talking about. We have the equivalent mud weight plotted on the horizontal axis, and the vertical and measured depths plotted on the vertical axis, right? So here we are looking at depth interval of the vertical parts of the well, and the highlights of this graph is so we can see how that claystone succession is prone to collapse and instability by looking at the gap. So between the gray area at the left side, which represents the pore pressure, and the orange very curved area, which is a collapse gradient. At the same time, being in the shallow depth environment, we have also the different colors representing the different probabilities of losses, basically having the loss gradient and fracture gradient. And here we also dealing with low figures, quite small margins, which is attributed to shallow depth environment. And we have an appreciation, right? It all makes the drilling window quite narrow for operating, and in the most tight place, we have just 1 ppg, like drilling window margin, which is quite interesting, and we'll share with you how we basically approached and dealt with that. Moving on, at the next slide, we want to show you the good picture for that visualizes, it gives you a well pad overview. So these are highlighted in red, 2 wells drilled during that 2020 year campaign. Wells by names 11R and 12R. 11 was the first one, and they're similar wells, but having different configuration of well trajectory in the horizontal plane, as we can see. And the 11R having the more complex trajectory, it has more reservoir exposure, more extended laterals, whereas the 12R, the second well, it has less reservoir exposure. We'll look at the figures further on, and having more fishbone type configuration of the well. They were both drilled in opposite directions, just to trade. That's was intentionally designed from the reservoir engineering perspective to be able to test different patterns of their reservoir performance, and also to avoid further well test interference.
Erik, I have a question, please.
Right. Okay.
Can you please elaborate a little bit more as to what was the logic behind different length of those laterals, of those branches?
Yes, of course. That's also coming basically from the project appraisal project objectives. As we were here, we're trying to estimate the reservoir potential. We also wanted to understand which performance would be delivered by the different horizontal configuration of the wells. To mention that reservoir properties are not they do not have equal distribution around the reservoir, and that was the main idea, to see and understand if increased reservoir exposure and horizontal meterage would really bring us any good benefit in terms of production output. Yeah, if you would see any very beneficial and significant associated increase in production.
And actually, it did. We confirmed that the bigger reservoir exposure, the 11R well with the highest drainage area, was producing accordingly more than the 12R well.
By the big order, even larger production output. And to give you more exact numbers of the reservoir exposure, here we have the key metrics presented in the slide. That's 11R well, and it has achieved 7,657 meters of horizontal cumulative length of all the branches together. And also interesting to highlight here that kickoff point is a critical shallow depth of 100 meters because we had to initiate the directional work as early as it was possible, following geological reasons. And another point to mention here is a sequence of branches. The way this configuration was executed was drilling the branch number 1 first, and as you can see in the label order, finishing with branch number 5, which effectively is the main bore, and which is the one was cased with a 4.5-inch liner screen, when all the rest branches remained open and not cased, not isolated. That was the completion strategy that we will also touch in more details further on in the presentation. And on this note, just to show the second well trajectory, more fishbone type configuration, right? More simple one, having just 3,245 meters in horizontal exposure. Yeah, and also the distances between sidetrack points for each lateral, they're also bigger here. And as Artur confirmed, yeah, that type of well did prove not really the best case for the project, and having the largest exposure being the best solution. Yeah.
Can you please go back?
Sure.
Another thing worth mentioning here, right? That both these two wells were built in two opposite directions. And in terms of geomechanics, as was already mentioned, our horizontal stresses are more or less equal in their absolute magnitudes and values. And this was actually confirmed by drilling conditions. That they were almost identical. So there is basically no matter in which direction you drill in our reservoirs in our area, the drilling conditions are same, and the behavior and all the problems associated are equal.
Moving on, it was also interesting during preparation of that presentation to give everyone an understanding and basically the confirmation from our side where do our wells where they fall in terms of categorization of that complexity of the trajectory. And here we plot in the red our wells over the industry-based benchmarking of all extended reach wells, also called the dog nose plot. And here we see, according to this categorization, that this type of wells, they fall closely to the border between extended reach and even extreme reach categories. From the previous pictures, it was not really, looking at that. It does look quite simple from the first glance, but when we look at the comparison between other extended reach wells, this shallow environment, it exactly why bringing this whole complexity and making the project not a standard, not a symbol, but quite interesting.
It might look even more interesting, if you sum up and take into consideration the whole reservoir footage that we drilled, the 7,645 meters, which will basically place us even further at the spot.
Right.
Somewhere here, yeah.
Close to 7.
If we'll count like this, this would be looking as a record for this TBD.
Yeah, it might be, but here we just presented the main bore. But if you're talking about summing up all the branches, yeah, it would look really extreme case. So
That's a good try, guys, but that's not how it works.
right, try to beat all that performance. But it's still interesting project that we want to move on sharing with you guys. And the next point to stop would be the well design. Just to quickly go through, from this side, there is nothing sophisticated. We're having the standard casing sizes and basically quite typical for West Siberia casing design configuration, which is three-phase design, not counting conductor, and 12.25, 9.5/8, and 7-inch casing sizes, and 4.5-inch liner screen, which was installed in the main bore and located in the way where the screens were in front of the most productive potential intervals, so to say. Right. At this point, I'll hand the word to Artur to continue with.
Yeah, thanks, Erik. After this introduction that you made, we'll go to engineering details. The first one will start with hydraulics. And hydraulic discussion, we would like to start with an issue, a challenge that we experienced at one of our offset wells that we drilled prior to this appraisal campaign. That was a horizontal well with 2 kilometer length of horizontal section. And that well was drilled with an oil-based mud for the first such a long well in the field. And what we can see at the first plot, to the left, this is the ECD plot, vertical axis. So we have the length in TVD and measure depths both in meters. And at the main part of the plot, we have our drilling window, global collapse gradients to the left, static density green line, and circulating densities in red line with the fluid loss gradient, the blue zone. Right. What the most important thing to mention is that the most typical issue for such type of wells as we drilled shallow ERD horizontal wells is ECD management. So we experienced exactly this issue, and in a hard way. So as you can see by the very end of the section, our static density was even less than the wellbore collapse gradient. So we experienced whole instabilities and cavings were observed at surface, and our ECD with pumps on was exceeding the fluid loss gradient, so we experienced seepage losses. We were losing quite heavily the expensive oil-based mud, and the main driver and contributing factor to this issue was the rheology of the fluid that that gave us such a high ECD. And in order to tackle this, we could only implement additional drilling practices, additional back reamings and circulation cycles, which overall made our drilling progress inefficient and rather slow. So, and having understood this challenge and generally the issue of ECD management at the planning stage of these two appraisal wells, 11R and 12R, we targeted and approached this issue in the following way. At this slide, so we can see at the very beginning we designed the new fluid system, which was water-based system versus oil-based used previously. Why the water-based? Because with the water-based system, we could reach the required much lower rheology numbers that were, if we could see here, the 6 and 3 RPMs of one viscosimeter numbers were both less than 1. It's very low numbers actually.
Yeah. So just to support what you are talking about, Artur. So the idea we came up with was some fluid with very thin rheology, and our basically the idea was why not we try just water and specifically the brine, and then how it all started going from oil-based mud to water-based mud and trying back this concept, but with significantly lower figures of low-end rheology.
Right. Basically, that was a viscosified brine.
Yeah.
And the first question that arose was how the formation would react with the water-based fluid. In order to answer this, we run a number of lab tests. First one was the immersion test, also called inhibition test, where we left the piece of core from our reservoir in the static aging at the reservoir temperature for 1 month. 1 month was a planned time to drill our horizontal section. And by the very end, we realized, looking at the results and comparing two samples before and after, that there was no any hydration and generally deformation of our sample, which meant that there is no any significant reaction between the formation and the design fluid. Another test that we run to confirm this was so-called at the right part of the slide, we can see EC test, cation exchange capacity test, which is basically their typical fluid methylene blue capacity test that tells us that the reactivity of our solids from our reservoir rocks are really low. And if we compare them against reference numbers of bentonite reactivities, they are much lower, which means that the formation is not reactive at all at the given concentrations of salts and other components of our fluid system. And the next question that we asked ourselves, right, was regarding the hull cleaning issues. Having such a low rheology of our fluid, would we be able to clean our wellbore sufficiently enough? And in order to answer this, we run a few hydraulic simulations in several softwares to double check, compare, and confirm results. And we ended up with observation that the flow regime in annulus was a turbulent one, that with the given planned drilling parameters was sufficient, right, to ensure and to grant good hull cleaning conditions. Positive indication that made us to feel on the confident side that our wellbore is going to be cleaned sufficiently enough. Yeah, next slide.
I have a question, please.
Yes, please, Olzhas.
What you showed just now was pretty impressive. I mean, the water-based brine, turbulent flow, perfect hull cleaning condition. It all looks great, and I wish it happens everywhere in the world. But my question is, those numbers are likely to be generated in a lab tests, and so, but very likely in reality, you had some cuttings dissolving in the mud anyways, and so the rheology must be keep growing up, and so how did you guys manage to sustain that low end rheology that would allow you to keep the flow in a turbulent regime? Because we all know that the moment you start adding a little bit of viscosity, you unfortunately lose that hull cleaning magic called turbulent flow.
Yeah, that's actually a very good one. Thanks, Olzhas. So an important one to mention, at the very start of drilling horizontal section with this type of fluid, we realized that we basically cannot control the fluid properties with mud conditioning and the solid control system. And the only thing that helped us was just a dumping of the mud coming out of the well, not the whole thing, not the whole return mud, but most part of it, and introduction into the circulation system, just a fresh volume of mud. It was a continuous dilution system established, like a closed loop circulation, that the fresh mud was has been built in a separate mud pit continuously was introduced in the section in the circulation system, with the return flow being diverted to the cutting speed, so that the half of it was dumped. And by this we have been controlling we've been controlling the dilution rate continuously, and monitoring our rheological properties, looking by the deviation of our rheology from the plant parameter. We basically increased or reduced the dilution rates. So this is how it worked, their rheology management. We could afford, in this case, this endeavor for ourselves. Why? Because it was basically, as was mentioned, viscosified water was very cheap, a rather cheap solution. If we were talking, comparing this with the oil-based mud that we used previously. Just what I want also to highlight here, that it was basically when we started from operational side during drilling of this well, looking at the behavior of ECD with when we first kicked off drilling the in horizontal plane. It was kind of trial and error to see how it all is going to develop, but I would say it also the specifics of our reservoir, which has everything, has claystone, has sandstone, and the case that the clay was not reactive, which was proved during lab testing,
and which really did take place. We confirmed that, and also we could observe that the rheology was increasing due to the small particles, which basically none of the solid control equipment apart from the shell shakers was involved in the mud cleaning process, right? And it was just building up this solid phase, which was not coming from the reactivity of the clays, but from partially from the grinding mechanical process throughout the whole horizontal interval with the string being rotated, and also having such a specific granulometric composition of the lithology that we have. It also worked quite in a synergical way in our case that we basically managed to cope with during operations.
Right. If you can see the results, yeah, at the next slide. So here to comment, we're looking at ECD trend. At vertical axis, we have meters. It's our measured depths in meters and in feet to the right, and X at the horizontal axis, we have ECD numbers in both SG and PPG. So we see basically the important thing is to note the trend. The trend was rather stable, and every single time the trend was deviating from the anticipated and planned and model curve, the dilution rate was increased, by thus bringing the ECD back to a normal anticipated model number. So the control was established rather good, and it was very responsive. That finally we did not have to implement any additional drilling practices and spend time for wellbore treatment operations such as back reamings, additional circulation times. So only dilution this helped us to manage ECD, to tackle this issue, and
we even did not progress. We never were varying the rate of penetration. So it was the only way was impacting on the mud.
Right. The only limitation basically for our rate of penetration was the LWD in GNG data acquisition quality and speed requirements, right? And by thus having this fluid system in place and such ECD management practices, the overall drilling progress was way more efficient in comparison with previous wells and offset wells. Same behavior we can see at standpipe pressure. The plot to the right represents standpipe pressure trend. Again, it was good match with the model anticipated numbers, same as ECD, and good control of it was established there. Going further,
Artur,
Olzhas.
Yes, going back, I'm reading through this list of ECD management measures, and I can see this number 4 where you say that no reaming, no circulation. Is it related to the final, cleanup cycles, or you're talking about the connection practices?
It's about connection practice. That's right. So basically, we drilled every single stand down and spending times only for the surveys, every single stand, and for weight measurements, every third stand, right? And monitoring closely the whole condition by our direct chart, hook load roadmap, and yeah, basically we did only the circulate bottoms up cycles at the very end of every single branch and at the very end of the main bore.
Just to mention those the end of each branch, the TD and the main bore, it was not like a circulating cycle. It was already the very slow back reaming and at the same time cleaning up. So we never we tried to make all the times progress, and which worked well, and we did not. Basically, what we wanted to avoid is redundant operations, which we achieved quite well right here. Yeah.
Interesting. Thank you.
Yeah, going further, we wanted to touch the base with the drilling mechanics. The plot that we're looking at is a hook load roadmap. Again, a vertical axis measured depths in meters and in feet to the right, and hook load numbers curves. The blue curves slack of weights, and the red ones plant curve for different range of friction factor, and the red curves pickup weights, again for different range of friction factors. And we can also see here the actual data plotted for pickup weights. The dashed lines, the green one, pink one, this represents the actual data from fishbone branch number 1, then branch number,
basically every
subsequent
branch.
Right, what we can see here,
Also red and red dots.
Yeah, red dots.
4 of them as 4 branches. That's
Correct.
picture of.
Right. So as soon as we're already here, I'll comment that we can see increase in the weight numbers from branch to branch, and the steady trend within one branch. So what does it mean? It means an increase in friction factor and different wellbore conditions with the further drillings of every single subsequent branch. How did we explain this for ourselves, and actually what it was? So potentially, as we assume, that was an accumulation of the cuttings with the drilling progress from branch to branch in the upper part of the well, in the intermediate section, and further on, from the back reaming process operation that we did when we tripped out from every single branch. And worth mentioning that the whole horizontal section was drilled in 2 runs. We had to trip out just for top drive saver sub replacement and BOP pressure test reasons, but
just exceeding its running hours.
Right. Yeah, there were no any issues, so the reason was just the running accumulated running hours that had to replace this piece of element. But anyway, we during back reamings, yeah, we basically brought all the cuttings upper within the wellbore and continued drilling with already increased amount of cutting and different hole conditions further on. That is why we can. This is how we can explain increase of friction factor, pickup weight friction factor from branch to branch. Talking about the slack of weights, we see no any actual data here plotted here because no any slack of almost none slack of measurements were taken. As soon as since we can see there was no any slack of tripping ability past the 2000. Yeah, even here, right, 815 meter depths. There was already buckling happening with the drill pipe, so without rotation we could not trip in. That's correct. Another thing to comment on is tripping out operation that we executed from every single branch and from the main bore. So here we attempted 2 types of trip out operations. The first one was just a pump out. We can see the response of drilling parameters during the pump out. Here we're looking at the hook load that was increasing against the expected and the modeled trends. The difference actually was not that significant. It was about I would say few tones, right? But still, the direction, the trend was deviating in a different direction than expected.
From my side, this is the hook load behavior. At the same time, during background operation, we close the amount of other parameters, oil pressure and ECD, which were responding in the same way.
Right. So basically, what it told us that we were dragging the cuttings by doing this up upper to the wellbore by tripping out a hole, and this warned us, and we were cautious in order to avoid making this situation even worse. And so what we did, we initiated rotation straight to turn on this conveyor belt to try and lift the cuttings more efficient way and safe way up in the wellbore. So you can see that the hook load numbers with the rotation, they decreased significantly, drastically to and matched with anticipated and model calculated parameters.
So interesting to know how significantly by
Artur,
Yeah.
one thing, please. We can hear you very well, Artur, but we can barely hear Erik. Erik has to move closer to mic, probably.
Okay, thanks. Thanks for the comment, Olzhas.
All right, and
Yeah,
then
just
the
a little.
and then the question, the clarification that I have with regards to your tripping out procedure. When you said you were pumping out, were you pumping out at the full flow rate, or were you just lubricating out of hole? And what was the reason basically to pump out rather than just trip out, just trip on elevators?
So during the pump out, we did not use the full drilling rate. That was the half, I would say, the half of the drilling rate, right? And the main reason to pull out hole with circulation was the swabbing concern. In open hole section, as we already observed in our this drilling window, we had a very narrow margin, and every single movement of the stream without circulation could induce a swab related wellbore instabilities and the whole collapse. So this was very clear and understandable for us at the very beginning, and that was forbidden for the drilling crew to avoid any movement with the stream without circulation in the well. So we could not afford ourselves this one. On the side of the difference and choosing between vacuuming and pumping out a hole, there was just an operational decision making. First of all, to be in the safe zone, and if any of the solution works, to go for the fastest one. And of course, pumping out of hole seemed to us like better in terms of easier control, and it seemed to us, and we tried
Easier and safer operation.
yeah, but indeed it didn't happen other way around. So we observed like dangerous trends
Near back of development.
back of security, and when we switched on rotation and proceeded with backrooming, that went more efficiently, even quite faster and safer for us. Yeah.
It's all about conveyor belt, boys.
Yeah,
It's all about trying different and
Right.
always having all eyes on the roadmaps, being prepared up front with
Actually,
with the simulation
that's a very
models.
good one. If we would not have this numbers and curves against which we were comparing and looking at, we would never, I believe, understood that we had this situation, development in our well worsening situation.
Yeah, and if we were to continue with pumping out of hole at the same flow rates and speeds, we would probably definitely
End up with a back off. Yeah.
end up with something bad. But luckily, we've
Luckily, we have KNM engineer on site.
and us as well. We're basically few engineers day and night looking at that plots.
All right, that's good. Another interesting thing to cover is the liner installation. At the planning stage, here I'll note this. The model. This is a liner hook load roadmap again. Liner run. We see here the slack of weights numbers. The vertical axis again. It's measured depths in meters and in feet. And yeah, right. This is a zero weight line. And the X horizontal axis, we have the weight numbers in tons and in pounds, kilopounds. We observed in the planning stage that at the worst case scenario, at the 0.4 friction factor, if we would have this condition in the well, we would not be able to reach with the liner to our target depths. And so we planned for since the very beginning for two contingencies to have two contingencies in place in case this situation will happen that we can rely on and implement. The first one was and that deployment of the downhole swivel. That was also one solution that we wanted to test and to perform the field trials at these two appraisal wells of this equipment of this tool. And another one was in case we would need to rotate the whole string to have the high torque connections at our 4.5-inch liner in place. So we had these two, but luckily none of this we had to implement to reach with the liner to TD. We can see that the liner, the blue line, the actual data, the blue line that we plotted against the model followed the minimal friction factor, indicating the favorable condition, and the lowest open hole friction factor of 0.2 in our wellbore. And at the matter of curiosity, in order to, as was mentioned, to test and to see how it works, the downhole swivel, we rotated the landing string itself and observed that like 8-ton hook load increase from 6 to 7, yeah, as noted here in the slide, from 6 to 7 tons increase in hook load. Yeah, during the run when we started removing this axial drag in the upper part of the well, which is quite significant, assuming the range of slack of weights we were having, right? 7 tons, and then increasing by twice. So it's a great result, and it did allow us to gather this. Yeah, so we can say that information. We can say basically, in case of more difficult and tricky complex trajectories for future development wells, should we need any contingency solutions, we definitely can rely on this downhole swivel.
Yeah, without any high torque connections.
Moving forward, a few words we decided to mention regarding the site tracking procedures and generally the kickoff point geometry of how we drilled our multilateral configurations, right? As was already mentioned at the trajectories overview, the sequence of drilling of our branches was starting from the site and going to the middle. From the branches were drilled first, finishing the horizontal section with the main bore, which was finally cased with the liner. The line and all the branches were left open. So here we can see in the horizontal plane how the branches were deviating from each other, but the most interesting part in the vertical plane. So what we can see here, the kickoff point geometries. If we have a closer look at kickoff point number 1, there are basically 3 pieces of parts of kickoff point. The first one is
to make it clear for everyone. Now we're going to be describing 3 different intervals of the branch.
Right.
So the way the very first branch is drilled already had special planning of that well path to allow for the successful site tracking of the subsequent one.
Specific geometry.
So, and these 3 intervals are the ones Artur is going to explain.
Right. So we're looking at the blue curve. We will follow the blue curve. This is, let's say, the branch number 1. The geometry of the kickoff point of the branch number 1 consists of 3 parts as follows. The first one is a false groove, which is placed here. False groove basically has inclination 1-2 degrees lower, degrees lower than the branch itself. Right, it's done specifically to, and the length of the false groove equal to the length of BHA, to have the BHA line a little bit down, and with the gravity force, it will working downwards.
When the next side tracking is done.
Okay, right. So the next part of kickoff point geometry of the branch is the ramp, the trampoline, against which the ramp and trampoline is just a sharp build interval of 6 degrees per 100 feet. And basically we gain here a few degrees in inclination. Let's say our horizontal section inclination is 90 degrees. False groove will have 88 degrees inclination, and then with the ramp we are gaining up to 91 degrees inclination. Right. This is done specifically again for the further operation when the BHA will be lying here in the fall groove to work against something, against the build, the sharp build. And the last element of the branch is a stabilization interval, where after the build we keep the inclination steady, and we can already work in different azimuthal direction as noted here.
So basically, after the stabilization interval, the real-time geosteering was taking place.
once all the critical directional portion of the branch was completed, specifically the false groove, the ramp, and the stabilization unit, then geologists were switched on and helping us to geosteer in real time. That's correct. Soon as the branch was drilled and backrimmed up to their kickoff point, again, the BHA was positioned in the false groove and then started to work downwards, strictly downwards. I think we have visual pictures that we can show, right? Right, that's correct. So basically 4 steps of side tracking. Here we can see BHA in the false groove working, making a so-called ledge. Ledge was made in the rotor steerable system in neutral mode, and using just the gravity force and circulation and rotation without any weight on the bit, meter by meter. The length of the ledge of this interledge building, it was about 3 meters. As soon as there was sufficient phase of formation worked out and built, we started to observe some torque, and then we could apply some weight, additional weight. And after that, the time drilling mode took place. Time drilling mode with steady parameters until the difference in inclination between 2 well bores was confirmed. When this was confirmed, difference in inclination, then the drilling parameters were increased, and then we proceeded in the full speed to drill the next branch. Olzhas, any questions on this side tracking operation here so far?
Well, it's very interesting what you're describing, and I'm just trying to draw this this image, and then you showed the slide, and now it cleared up. So liner will always be seeking the low side of the hole, and this is where every other branch is drilled pretty much. It's always on the low side. So that's the reason your liner will always be going into the wellbore that you want to complete.
That's correct. That's absolutely right.
I have a question. Have you had any contingency plan? Say, for example, for one reason or another, the liner would end up going into the wrong branch. Was there any way that you would find that it's in the wrong branch?
That's right. The first one, the comment that you made is that the liner, when it's run, will always follow the path of the least resistance and going down under its weight, right, under its gravity. This was the idea behind drilling the main bore in the last order. And answering the second question, so we had all the branches of the slightly different lengths with the different TDs. In order to understand by the liner running tally that we end up in the desired one, in the designed main bore, in the designed branch. If we would end up in the different one, which was basically unlikely, right? But anyway, we would understand this by the running order, that we were planning and controlling at the rig.
Yeah, fair enough.
Yeah. So we go further. Another and the last part that we would like to cover, and very also interesting engineering moment, was related to upper completion installation, upper and intermediate completion. Basically, for us, for our wells, this 11R well was tested, and their intermediate and upper completion string was represented by ESP pump that was run on, we can see here, right? ESP pump was run on 3.5-inch tubing above, and it had also the tailpipe 1.9-inch tubing tailpipe below that acted as a carrier of DTS cable. DTS stands for Dynamic Temperature Survey. So basically, sensing, yes. Basically, we monitor temperature during production to assess the contribution of every single branch into the whole total well production. Right. This was intermediate completion. Everything that below ESP pump, this 1.9-inch tubing with the DTS cable. Also, there were some pressure gauges, 4 pressure gauges within this intermediate completion, and above the upper completion part was represented with ESP pump itself and 3.5-inch tubing. At the planning stage, we observed the very interesting situation that
just to mention, that was the first time we planned such kind of completion, and specifically in terms of torque and drag, and checking if that whole assembly would.
Yes, the main point is that at the planning stage there were no any history data available that we could rely on and have a look, and we are basically referred to the rule of thumb and typical industry numbers for friction factors, for case hole friction factors. So what we are looking at is the again hook load roadmap running whole this completion string. Vertical axis again, this is measured depths in meters and feet, and horizontal axis are the weight numbers in tons and kilopounds. Upper part represents a 7-inch casing, where we had 0.2, I would say 0.2 right fixed friction factor, and the lower part of the well is 4.5-inch line, where we run the tailpipe. This part of the graph, and we see here that at different numbers of 4.5-inch case hole friction factor, we have different situations. So we're understanding that we could install completion with a 0.2 friction factor in place, and in case it was the whole condition was worse and friction factor was higher, the tail pipe would lock up, and we realizing that we could end up with this and not reaching the completion string to target depths. That is why, having this understanding, we started our operations with a dummy run of this completion string, and in order to assess generally, to confirm the whole conditions, we realized that it was as bad, the whole condition was as bad, and the friction factor was as high as even 0.4.
Right.
This is calibrated. The 7-inch whole friction factor was calibrated even at 0.1, right, and 4.5-inch case hole friction factor was calibrated at 0.4 with a tailpipe lockup happening in the 7-inch casing, right, where it has more space to buckle.
And the way we figured it out is really doing the
So
analysis. Yeah. And trying to identify all these trying to solve and understand what's going on during this demo run, potentially trying to find that solution.
Yeah, basically we can see the issue at this simplistic schematic, how the tailpipe was buckling in 7-inch casing during the run.
Erik, for some reason we still cannot hear you very well.
I'll try to talk closer to the microphone.
Yes, please, yes. But please, just one question. So you guys run this dummy run, and from what I'm seeing, your say 7-inch case hole friction factor followed a certain trend, and then once this tailpipe entered the 4.5-inch liner, all of a sudden I can see that those black dots, start following different trends, and then ultimately at 2250 or 2300, it seems like you run out of weight, or not
That's
run
correct.
out of weight. I would say run into the lockup condition, right? So
Yeah, that's correct. Absolutely
how would
right.
you explain this? I mean, because this is a little bit confusing, right? When you're running your pipe inside the cased hole, people
Yeah.
would tend to believe that there's no cuttings, there is no wellbore instability. If there is wellbore instability in your casing, it must be some nasty wellbore instability, right? So
Right. Actually,
supposedly the hole must be in a great condition. So why wouldn't the pipe run into the hole? So in this case, what did you guys derive to? Like, what was the reason?
yeah, that was also our misunderstanding at the planning stage. We were hoping that case hole, even 4.5-inch case hole, will give us like favorable and good hole condition and low friction factor. But indeed, it appeared to be the tight clearance the reason of this issue, that when 1.9-inch tailpipe entered the 4.5-inch liner, it encountered much bigger and higher resistance, and we in a few hundred of meters we already run out of weight, as you said, and entered in this tailpipe buckling, which locked, as I said, looking at this effective tension plot. The lockup occurred in the upper part right below the pump, but due to the resistance in the liner below, the lockup happened upper in the 7-inch casing, right? But the main reason to that, as we understand, was a tight clearance between the tailpipe and the 4.5-inch liner. It was the reason to that. And how
Absolutely.
we
This
basically,
is
yeah.
Sorry to interrupt you. I just wanted to make this little note that you're absolutely right. There is some sort of misunderstanding or misconception where a lot of people believe that the friction environment in the case hole should always be more slippery than in an open hole. But in this case, we can see that tight clearance actually drives your dynamic friction factors. The tighter the clearance, even if it's a cased hole, you may still run into the high friction environment, as high as 0.45, just like you showed us with the failed dummy run. So yeah, don't always assume that your cased hole friction factor are always lower than open holes. The different
that was
clearance
exactly
environments would drive the numbers. Yeah.
that was one of the biggest learning for us from this project during the dummy run. Yeah, that was the first dummy run when we confirmed our worst case scenario, and then we had a backup contingency plan in place. How we basically get out of the situation. We planned for flotation option of the tailpipe in order to gain some weight. So what we did, we entrapped air inside the tailpipe as soon as it was acting solely, so only at the carrier of the opto fiber cable and the pressure gauges. Then we did not need to use its internal area ID for any circulations, just a carrier. So we isolated and basically sealed the air inside.
We used just
and floated by this.
It was nothing sophisticated. We used just the blind collars from each side to trap air and basically to drop some weight of this. Yeah.
Right, and it worked well indeed, and helped us to deliver. As we can see, the actual data were plotted here. Already different model for the case with flotation, and the actual data followed the 0.35 friction factor in 4.5-inch case hole, and same matched before 0.1 friction factor in 7-inch casing. So this is how we basically managed to solve our issue with the tailpipe buckling and lockup, and that was a successful second final run. Yeah.
This is very interesting, guys. So just to summarize what you just said, run the tailpipe, 1.9-inch tailpipe. You run it empty. You pretty much floated it, and then the tubing and the top part actually mud filled, right?
That's correct. Absolutely. The upper tubing above ESP, 3.5-inch tubing, was mud filled. As conventional and yeah, and the only the pipe below was floated with air.
Interesting. You guys replicated the casing flotation, but using the tubing
in a simple way. Yeah.
Perfect. No, that's pretty smart.
No, yeah, we just copied some
best practices
and try to make the best out of it in circumstances we had.
Yeah, I would say that this is everything what we wanted to share with community today.
Oh.
Yeah, thanks everyone for attention and for questions. Olzhas, I don't know if we have any other questions anywhere in the chats.
Let me check the chat if we have any questions. I have the chat up running so far. There are no questions. People just sending some nice comments to you guys. But anyways, thank you very much for this nice presentation. I really enjoyed it. It's pretty interesting project with some, even though it looks simple at a first glance, but once you start looking at specifics of ECD management, of tripping practices, of side tracking technique, and eventually even this liner run and the upper completion run challenges, that makes this well not really trivial, right? So it's thank you very much for sharing your observations and your learnings. I hope the guys who attended the call will enjoy it as well.
And again, right, from Repsol side, many thanks to K&M being a part of our project and of the success story, right? And of this very good and valuable learnings. And again, for this opportunity to share this with everyone. Yeah.
Well, thank you guys. Thank you. Let's ask the audience. Audience, if you guys have any questions, please type them in a comment section, and we'll try to respond them. And let me do this typical standard statement over here. Since we are on a social media, if you guys enjoyed the show, the episode, please make sure to click the like button and share with your friends. Well, from what I see, guys, we don't have any questions so far, and we slightly run out of time, so it might be.
Anyway, I'll just. Do you know if this recording is going to be available for watching at a later stage? Maybe
Correct.
if there are some other questions come up, we can look up. And if there are going to be any questions, they could be addressed via LinkedIn
in the comment section, right?
Or in the comment section that we will be looking for a few weeks after that, and we'll be glad to address them.
Appreciate it. That's a very good comment. Yes, those recordings will be available on LinkedIn as well as on YouTube. So yeah, anyone who will have question or clarification to you guys can drop a line, and yeah, you can revert back.
Yeah, perfect.
Well, thank you very much. I won't take more of your time. Really enjoyed the presentation, and yeah, keep safe.
Thanks, Olzhas. Likewise, same to you and everyone. Cheers.
Yeah, have a good day.